Hello. Today we're going to begin vectors. In this video, we will just be doing basic properties of vectors. In later videos, we'll move on to dot product and cross product. Okay. I'm going to give you a rough definition of a vector. It's not a precise definition. The precise definition is really abstract and it's not that useful to us. So I won't put it in this video, but if you're curious, you can ask me about it. If you take a class in linear algebra, you should see the real definition of a vector. So the usual rough definition of vector that you'll see is a quantity with magnitude and direction. So here's some examples. One example is a velocity, such as a velocity of the wind. The wind could be coming from the northwest with a speed of 30 miles per hour, and the speed is the magnitude. From the northwest, it would be the direction. Another good example is a force. Someone could push on something with a force of like 100 pounds from the east direction. So those are some familiar examples. And when we work with vectors, we often call a number a scalar, just to emphasize that it's not a vector. And when you're working with vectors, it's important to always be clear about which things are vectors and which things are scalars. Mixing them up is a big source of problems. So if you can do that, it'll help you a whole lot. Now this definition isn't great and it has some drawbacks, and we'll probably see those today. Okay, so when you sketch a vector, this vector is sketched as an arrow. Oh, and it's purple, that's nice. And the name of the vector is either in boldface or has a vector symbol. And I'm a real stickler for the vector symbol. If you don't write the vector symbol, I'll take like a point or a fraction of a point off. And students lose so many points over the course of a semester. I'm sure there have been students who have gotten I'm sure there have been a couple students over the years who have gotten a lower grade as a result of omitting the vector symbol hundreds of times. Okay. If you're reading a book, then they'll use boldface for a vector, but you can't write in boldface. So if you're working by hand, you need the vector symbol. Now, there's one vector that doesn't look like that, and that is the zero vector. And the symbol for that is a 0 with the vector symbol. And my computer just went black for a second. So that was fun. Okay. So that is a zero vector. And it has a lot of, well, some properties that are similar to the number zero. And one of the most important is if you add it to any other vector, nothing happens. Oops. So v plus 0 equals v. Or any vector v. And I didn't write the word vector there because I wrote the vector symbol, so I don't need to write the word vector. All right. So whenever you're working with vectors, and there are lots and lots of different kinds of vectors, we're only going to be working with 2 or 3 dimensional vectors, but there's a whole, there's a much more abstract definition. But with any vectors, there are 2 things that you have to be able to do with them, and that is adding them together and multiplying a vector by a scalar. And we're going to learn how to do those things graphically first and draw the sketches, and then we'll do as much as we can with just sketches, and then we'll use numbers and components and I, J, and K. But for now, we're just doing it using sketches. So suppose I have a second vector. We draw another vector. That one's V, so I'll make this one, make this one W. Oops. Okay. Now to add them together, I draw one, and then I draw the second one at the tip of the first one. Okay, and then the sum goes from the initial point of the first vector to the terminal point of the second vector. And I don't care about that vocabulary, initial point and terminal point, but you might see it. All right. So that green vector is V plus W. You can also subtract vectors, but before we do subtracting vectors, we have to discuss multiplying vectors by scalars. So. Let me see what's in the paste buffer there. Only, I'm going to sketch a couple examples and then write a couple words about it. So that's the vector W, that blue vector. I'll draw a couple scalar multiples of W. Let's try 2W. Okay, close enough. So, okay, so that's 2W. Let's try 1/2 W. Okay, so 1/2 W has the same direction, but is half as long. You can multiply a vector by a negative number. So negative 3W might look something like that. I'm just eyeballing it. I've tried to make it 3 times as long. I'll try negative W. That should have the same length as W. Finally, 0 times W. If you multiply any vector by the 0 scalar, you get the 0 vector. Okay. Now, let me try to put this into words. And before I do that, I should say a couple things about length of a vector. It's kind of hard to define length of a vector. Sort of an axiom of certain kinds of vectors. It means what you think it means. But let me write down the notation and a couple properties. Oops. Now this is the notation I recommend. If you put a vector inside double bars, that's the length of that vector. Now the length of a vector is always non-negative. Okay, so any vector has non-negative length, just like the length of any object is non-negative in everyday life. And the only vector with 0 length is the 0 vector. Now, unfortunately, in my opinion, our textbook uses single bars for the length of a vector. So I can't penalize you if you use single bars. Now, for some reason, students almost never take my advice. Students use single bars, but please take my advice and use double bars because you'll thank me later. The reason that double bars are better is that it emphasizes that what's inside is a vector. Single bars is the same symbol as absolute value. So if you have some complicated expression and it's inside single bars, it might not be obvious whether it's a vector or a scalar. I write down in words what multiplying a vector by a scalar does. I don't know how to type this, unfortunately. Okay, so if C is a scalar and W, well, let's make that a V, and W is a vector, then I'll describe CV using its length and direction. Its length is the absolute value of C times the length of V. Okay, I wrote a star there. It means multiplication. I didn't write a dot because very soon we'll be doing dot product, and I want to emphasize it's not a dot product. It's just a product of two numbers. I'll bet if I wrote Phil Rizzuto, it would be easier than this. All right. Vertical lines are the worst. All right. Notice C is a non-negative scalar, and the length of V is also a non-negative scalar. So their product is a non-negative scalar. So that's how long CV is. Now its direction depends on the sign of the number C. So if the number C is positive, then it, meaning CV, points in the same direction as V. If C is negative, it points in the opposite direction. Well, what if C is 0? So 0V is always the 0 vector. The 0 vector doesn't have a well-defined direction. So that is one drawback of this rough definition of a vector as a quantity with magnitude and direction. The 0 vector is a vector and it doesn't have a direction. That's one reason that's a rough definition. And here, if V is the 0 vector, then CV is 0. I should probably write that down. So 0 times V is the 0 vector. And any number C times the 0 vector is the 0 vector. And I add those separately because the 0 vector doesn't have a direction. So that's how you multiply a vector graphically by a scalar. Now we can subtract vectors. Oh, Okay, I can do boldface. Okay. I have to use the mouse to do boldface, but well, subtracting the vectors works the same as it does with numbers. So v minus w is the same thing as v plus negative w. Let's George Michael that. Make it big. Or Tom Hanks that, if you prefer. George Michael's a slightly more topical reference, though. And I didn't care for the number Big anyway. I mean the movie Big. Not a huge George Michael fan, but not a fan of the movie Big either. Oops, sorry. Let me copy that. Copying things is often easier than doing original work, as you probably know. So let me sketch v minus w. So if I have to, I copy v where I want it to start. Oop, sorry. Okay, now I draw negative w, starting at the tip of v. I just got to, oops, let's make it the same color. I've got to eyeball it, try to make it go in the exact opposite direction as w. Probably should have used a grid rather than lines. See, I want to move it. I want to move it. I want to move it. No. I don't know how to move things. So. Oh, damn it. Okay, that's better. Okay, close enough for government work. Okay, that's negative w. Now I'll sketch v minus w. Okay. Okay, so that is v minus w, which is the same thing as v plus negative w. Okay, so that's how you subtract vectors graphically. Something I probably should have said before is you can add 3 or more vectors by connecting them in a chain. So let's define a third vector. See, x, y, and z aren't the greatest names for vectors. Let's go back to back to A. So that's the vector A. I'm going to sketch BWA. Let's try the See if I can do this by cutting and pasting. Okay, there we go. So that's V. Oh, crap. They'll get better, I promise. Okay. Yeah, this vector's in a, damn it. Okay, I'm just gonna draw it. Sorry about that. The vector is in a rectangle that has a background that's not transparent, which is really weird. Okay, so V looks like that. Oop. Okay, W, something like that. Finally, A. Okay, A is like that. Now for VWA, I'm sorry, V plus W plus A. Have to say plus. VWA isn't a thing. So V plus W plus A. It's that long green vector. Okay. And now vector addition is commutative and associative, just like addition of numbers. So you can group, oops. If you group them, have like V plus W plus A, that's the same as V plus W plus A. Since those are the same, we don't even write parentheses unless we want to emphasize something. And for the commutative means that it doesn't matter which what order you add things in. So V plus W is W plus V, just like with numbers. All right. So far we've added and subtracted vectors and multiplied them by scalars. Something that's worth thinking about, I should have mentioned a few pages ago, is the triangle inequality. Now, the length of vectors is not a linear operation, just like most functions are nonlinear. Let me write what that means. Oh, I guess I could have typed that. So in general, the length of v plus w is not equal to length of v plus length of w. I don't want that to be boldface. Okay. I don't know how to make a not equal symbol. So I'll draw that by hand. Make it black. Paint it black, as the Stones would say. I'm not really painting, I'm just writing. Should have saved that joke for another time. All right. So in general, the length of v plus w is not equal to the length of v plus length of w, because it's almost always, that equation is almost always false. But something weaker than that is true. For all vectors v and w, the length of v plus w is less than or equal to length of v plus length of w. So that's why it's an inequality, because it's a less, it's not an equals, it's a less than or equals. The reason it's called a triangle inequality is that because of this. If you draw v, w, and v plus w in a triangle, then v plus w, these three numbers are the lengths of the three sides. And the length of any side of a triangle is not less than or equal to the sum of the other two lengths. Now this inequality is almost always a less than. I think I can type that. So I'll do us all a favor and type it instead of trying to write it. Oops, sorry. The length of v plus w is, it's less than length of v plus length of w. Oh, sorry, got it right the first time. They're equal only if v and w have the same direction, or if one or both vectors is the zero vector. Okay, so that's a triangle inequality. So what else can we do with vectors purely geometrically? One thing that we will need to work with is unit vectors. a unit vector is a vector that has length 1. I had a French teacher in college that said you should only use the word whose with things, with people and not with things. So I didn't say a unit vector whose length is 1. That would be fine in other languages, but I guess if you want to be pedantic, you shouldn't say it in English. Now, something that you have to do once in a while is take a vector that's not a unit vector and scale it so that it is a unit vector. And let me show you how to do that. Where's my shape thing? Oh, there it is. I only need a 2D picture for this. So I need some scaling. Let's use it larger. Let's make, oop, duh, yeah, should be 1. All right. So suppose we have a vector that's not a unit vector. Let me be really creative here and call it V. Say that's not a unit vector. Obviously, its length is about 5 units long. Okay, I'm making these vectors boldface just because I can when I'm typing. Okay. So it's a fact that if you have a, let's make this bigger, add some more space. So if V is a non-zero vector, okay, that was my 5-minute warning. I'm going to have to wrap up this video in a minute. So if V is a non-zero vector, then if the vector V divided by length V is the unit vector in the same direction as V. And often people use a hat over a unit vector to emphasize it's a unit vector. It's not mandatory, but it's a good idea because it reminds you that it's a unit vector. So you scale the vector V by dividing it by its own length. And obviously you can only do this with a non-zero vector V because you can't divide a vector by 0, just like you can't divide a number by 0. So let me sketch what you might look like. I know what you look like. what the vector U might look like. So I don't know what most of you look like, really. So it'll go in this, the same direction as V, but have length 1. Now, when you draw a vector, you can draw it starting anywhere you want. The origin is as good a place as any. I'm going to have to eyeball this and try to make it 1 unit long and parallel to V. That's too long. See, when I pick up the, geez, one more time. Pretty good. Okay, so you might look something like that. Oops. Oh, crap. Now, you can just, so for example, if the vector has length 3 and you divide it by 3, you get a unit vector. Let me justify this. You can actually justify this if you believe everything I told you before. Well, one thing I have to do is, and this is something like only a mathematician would worry about, so we're not going to belabor it. If you have a vector V and you divide it by a scalar K, that's 1 over K times V. Okay. That should not be a surprise. Now I'm going to prove that U hat really is a unit vector. Okay, so length of U hat is the length of V over length V. V over length V is the same thing as 1 over length V. So now I have a scalar times a vector. So the length of that is the absolute value of the scalar times the length of the vector. Okay. Now, the scalar inside the absolute value is positive. And if you take the absolute value of a positive number, it stays the same. So those absolute values are unnecessary. So this is 1 over length V times length of V. And finally, that simplifies to 1. I'll draw a little filled in square. That's my filled in, that's my QED thing. Now, this always confuses the heck out of people. So if it does, don't worry about it. You don't need to know it. But if you do understand it, it may help a little bit in the long run. Now, if this is confusing, think how much more confusing it would have been if I had used single bars for vectors. So here I have double bars around vectors and single bars around scalars for absolute value. So I think this is a good place to stop. With the next video, we should finish. We've done just about everything we can do just by drawing pictures. And the next video, we'll begin using components and numbers and have actual specific vectors with numbers in them. And it'll be less abstract than this was. So I will see you shortly. If I can figure out how to end this.